Okay, so we are at the start of our plate tectonics unit. And so in order to understand plate tectonics, we have to start with the foundation of understanding about Earth's layers. And so when you were in elementary, you probably have heard before crust, mantle, core. And so what we're going to be doing is getting more sophisticated in our understanding of those layers. Plus, we're going to learn a second system that's really important in our study of plate tectonics. So let's start with this. I have an image here of an apple. And you might be thinking like, why would you put that there? Well, think about our planet and how it's kind of like an apple. Okay, so just like an apple has layers, so does an apple. Or excuse me, just like the earth has layers, so does an apple. And the other thing is, if you think about the layers, have you ever just peeled an apple and tried to get the skin? It's very, very thin. That's similar to the crust. The inside of the apple is called a core of the apple, just like the inside of our planet. And so the first system that I'm going to be teaching you is based on composition. And when I say composition, here's what I mean. I mean what it's made of. By the way, folks, after you listen to this or simultaneously, meaning as you listen to it, you're going to be answering some comprehension questions about this. So anyway, when I say composition, I mean what it's made of. So the composition of lasagna is like cheeses of different kind. And did you know there's egg in there and noodles and usually it's meat and marinara sauce. So that's the composition of lasagna. The composition of a layer of our planet means what it's made of. And so you can see that this is the system you've heard of: crust, mantle, and core. So let's start with a little bit of data. Just like the skin of the apple would make up less than 1% of the mass, that is like the crust, less than 1% of our planet. And here's what's kind of weird. Scientists still, even though they're trying, cannot drill down into the mantle. So the part of our planet that we've explored firsthand is really just the crust. Well, we'll get to that. There's a little bit of a difference there. But anyway, we cannot physically drill into the mantle or the core. Now you can see the mantle makes up 67%, the core 33%. Now for my math wizards out there, you're adding that up and you're going, Mrs. Fickus, that's more than 100%. That's 101. Notice this says less than, right? So about 67, about 33%. So I do expect you to know that the crust is the least massive and that the mantle is the most massive. Now, we start getting into some specifics about the crust. And even though the crust is the thinnest layer, we know the most about it because we have access to it. So there's actually two types of crust. When you think about our planet, if you look at a globe, there are two things that stand out: the water and the land. And so it is easy for students to say, oh, yeah, like I walk on crust. But here's what's also true. If you've ever been to the ocean and you're walking on the ocean floor, you're actually walking on crust there too. So here are the names of the two types of crust, and they are not tricky. They kind of define themselves. Continental crust is what it sounds like. It's the crust of the continents. And oceanic crust is the ocean floor. It's the crust on the oceans. If we could take the water off of our planet for just a moment, you would see crust there, and you would see different mountains, volcanoes, valleys. All those landforms we see here on our continents also are reflected in the ocean floor and the oceanic crust. Now, we're going to be learning three differences between these types of crust, and I want to start actually with thickness. Now, I'm going to say something twice because it's a little tricky at first. The crust begins where the mantle ends. Listen again to that. Crust everywhere on our planet begins where the mantle ends. So when you think about, okay, why are the continents, like why aren't they underwater? It's because of this fact. The continental crust is physically thicker, the oceanic crust is physically thinner. So the thickest crust on our planet would be the tallest mountain, and the thinnest crust on our planet would be the bottom of the ocean at the deepest part. So there's a definite thickness difference. Now here's another thing that's important in our study of plate tectonics. There's a definite density difference. So even though continental crust is thick, the molecules are more spread out, so it's less dense. And then oceanic crust, even though it's thinner, the molecules are more packed together, and we call that higher density or more dense. Now, here's the next step. You know that I drink a whole lot of this, Coke Zero. And so Coke Zero and Coke, are they made of the same thing? Not quite. And they don't have the same density because of that. One can float and one can sink. So now if we think about this, if there's a density difference between continental and oceanic crust, are they made of the same thing? The answer to that is definitely no. So continental crust is made of silicate minerals. You remember silicate, right? Quartz, that clear pointy crystal, where oceanic crust is made of more dense native elements. Now, native elements are things like iron, copper, and lead, and those things are non-silicates. Okay, so you're like, geez, Mrs. Ficus, there's a lot on this little skinny layer, just because we know the most about it. So now we go to the next step. What about the mantle? So scientists know, and you might be like, wait, how do scientists know? I thought you just said that we cannot drill into the mantle. Well, they know that it's a lot of iron and magnesium, and here's how they know: from volcanoes. So when volcanoes erupt, those extrusive igneous rocks actually provide mantle material at the surface for us to analyze. So even though we can't directly go there, we can directly analyze what the mantle is made of. Now, this last part is more of an inference, but it is a strong inference. Scientists know that Earth's core is made of iron because Earth has a magnetic field. Iron is one of just a handful of magnetic elements on our planet. And obviously, there's iron toward the center of our planet. So that center core of iron. So that is our traditional three-layer system that goes crust, mantle, core, and that's all based on changes in what the layers are made of. But now I'm going to teach you a more sophisticated system. By sophisticated, I mean a little more complicated. So I know that you're at home, but I want you to say these layers after me because some of them are weird. Ready? Lithosphere, astenosphere, mesosphere, outer core, inner core. Okay, now say them with me faster. Lithosphere, astenosphere, mesosphere, outer core, inner core. Again, real fast. Lithosphere, astenosphere, mesosphere, outer core, inner core. This is the 5-layer system, and I will show you side by side in a moment diagrams of them because it's still the same planet. So what is the different deal with this? Well, here's the deal. The 5-layer system is not based on composition. It's not based on what the layers are made of. It's based on how these layers react to temperature and pressure change. Okay, so I want you to do this. I want you to put your hands like this. So here's a solid rock with the molecules pretty close. Well, when that rock heats up, the molecules get farther away, less dense, and want to become a liquid. But then when pressure increase comes along, it takes those molecules that are spread out and makes it want to turn back to a solid. So this 5-layer system is all about a battle between temperature and pressure. Okay, so here it is again, right? Tightly packed solid rock. Oh, it's getting hotter, molecules spreading out to be a liquid. But then an increase in pressure can take a really, really hot liquid and turn it back to a solid. Okay, so let's check this out. The hottest layer on our planet is the inner core. Now, what do you think about the most pressure? Well, here's the catch. It's also the inner core. Do you see that popping up there? And so the inner core is not only the hottest, but it's also the most pressure. So if the temperature is winning, it would be a liquid. But if the pressure is winning, it would be a solid. And so we're going to go through each time and declare a winner in the battle between temperature and pressure. Okay, so when we walk on the lithosphere, it's almost like saying we walk on the crust. And so we know that the crust is solid, the surface we walk on. Okay, now here's some good questioning. Which is higher temperature out of lithosphere and astenosphere? Well, you should say astenosphere. Closer you get to the outer core, higher temperatures. Okay, which is under more pressure, lithosphere or astenosphere? It's the astenosphere. It has the lithosphere pushing down on it. So if I tell you temperature wins, you're going to say, oh, liquid. If I tell you pressure wins, you're going to say solid. Big reveal. What, Mrs. Ficus? What do you mean by jelly? Well, here's the deal, my scientists. It's a tie. Okay, so both the pressure and temperature increase, but at the same proportional rate. So this astenosphere, we are going to refer to it and sing about it soon as jelly-like astenosphere because it's not quite a solid, not quite a liquid. It's in the middle, kind of wiggly, kind of fluid, but not like spilling a glass of water. Okay, now, ready? As you get closer to the inner core, temperature up, pressure up. So if temperature wins, liquid mesosphere. If pressure wins, solid mesosphere. Here's the reveal. The mesosphere is solid. So what was the winner? Was it the increase in temperature or the increase in pressure? They both increased. The answer is pressure increased more. Okay, here we go. Keep that pattern. The outer core has a higher temperature than the mesosphere and more pressure. Which one wins? It is a liquid. It is our liquid layer. That tells us that what was the winner? That tells us that the temperature won. Now, finally, the very hottest layer on our planet is the inner core, but it's also under the most pressure of all the layers pushing down around it. This is shocking to some students. The hottest layer is a solid. And if you're like Mrs. Fickus, how could the hottest layer be a solid? It's because of the intense pressure that's holding those molecules close together. Okay, so you're going to use this to answer those questions if you haven't been already. You can skip to any point in this and listen again. But to finish, I wanted to show you a couple of diagrams. So this is the same planet, right? So here's like a cross section of the crust, mantle, core. Now in the 5-layer system, and I think this makes good sense, the outer core and inner core together equal the core. So is the entire core a liquid? Just the outer core. The inner core is a solid. Now the mesosphere is a solid, so that tells us the bottom of the mantle is a solid, but the asthenosphere here is more like jelly. See how the lithosphere and crust are similar. Those are solid. Okay, now the reason that I picked this, it still has crust, mantle, core, and then our 5-layer system, but I really liked how this was dealing with the differences in oceanic and continental crust. Do you notice here where my cursor is, that would be the continental crust. And then here, the thin crust is the ocean floor. That's the more dense oceanic crust that's made of those non-silicate native elements. Here we've got the thick but less dense continental crust. All right, and that's the end of the Earth's layers diagram. We will hear these layers a lot more in our unit on plate tectonics.